I've chosen to break up the introduction to E2 reactions into two separate videos. In the previous video, we talked about the fact that E2 reactions are regioselective. Right? This tells us about where the double bond is going to go. We also talked about the fact that E2 reactions are stereoselective. Stereoselective tells us that generally the E isomer is preferred over the Z isomer. And what we're going to talk about in this video is that E2 reactions are sometimes stereospecific. And so if there's only one beta hydrogen, we won't get both the E and Z isomers. We'll only get one of them. And we have to kind of picture the molecule in 3 dimensions and do some rotations in our head in order to figure out which one we're going to get. And so that's going to be the topic of this video. All right, on the previous slide, we looked at an example where an E2 reaction was stereoselective. I could make 2 different stereoisomers, but one was preferred over the other one. What we want to talk about now is slightly different. This is stereospecificity, where only one stereoisomer is produced. And so if we had this molecule and we were going to do an elimination reaction on it, right, we've got a beta carbon here, but it doesn't have any hydrogens. We have a beta carbon here that has a hydrogen. And so we might expect that we should be able to produce both the E and Z isomer, right? Where we could have, the tert-butyl and the hydrogen here, where higher priority groups are here and here. They're across from each other, so this is the E isomer. We have both high priority groups on the same side. This is the Z isomer. It turns out this isomer is in fact not formed at all, and we only form this product. So to understand this, we need to consider the structure and the mechanism of E2 reactions a little bit more. All right, so what drives this stereospecificity is the fact that at the transition state of the E2 reaction, the halogen that's leaving and the hydrogen that's leaving and the 2 carbons they're attached to must all lie in the same plane. And this is necessary for the electrons in these bonds that are going to become the pi bond. They have to be perpendicular to the rest of the molecules. And so these molecules all need to, or these atoms all need to be in the same plane. Right? In other words, the beta hydrogen and the leaving group must be what's called coplanar. They must all lie in the same plane. All right, now there are 2 ways that we can get the bromine and the hydrogen in this case in the same plane. They can be in this configuration where essentially they're trans from one another, or they can be in this configuration where they're essentially cis to one another. Now, if we think about the stability of these 2 structures for the transition state, this one, if we look at the Newman projection, we would expect to be much lower in energy or much more stable than this configuration where the hydrogen and the bromine and all these other groups are eclipsed. So this is what drives the stereospecificity. We want the leaving group and the hydrogen to be in an anti-configuration as opposed to in an eclipse configuration. And so then, right, the arrangement of these groups in the anti-configuration determines, right, where the groups are across from each other on the double bond. And so in this case, right, the methyl and the T-butyl are going to be on the same sides, and then the benzene ring or the phenyl group and the hydrogen will be on the same sides. And so this is the only isomer that we get. We don't get the isomer where, these guys are swapped from one another. Now, in reality, we don't have to be exactly planar. They can be shifted a little bit. And so the term that you'll see most often, rather than calling them coplanar, is we use the term anti-periplanar. All right, so if we wanted to predict the products, right, here's our leaving group, here's our hydrogen, and so the atoms or the groups on the wedges are going to be on the same side of the double bond, and then the dashes are also going to be on the same side of the double bond. So our product in this case is going to be right? And then the R1s are going to be on the same side. And then the R2s that are on the dashes are going to be on the same side. All right, and in this case, on the bottom here, right, so we're losing the hydrogen and the bromine again. So now, right, the ones on the wedges are going to be on the same side. And so I'm going to have R1, but now the wedge is on R2. And then going back, I've got R2, and then R1 would be here. Now, in this case, they've made it pretty easy for us in that they've drawn it so that the bromine and the hydrogen are already periplanar, and they're already anti-periplanar. The molecules won't always be drawn to make it this easy. And so I've got another video where we look at some more examples of drawing products of E2 reactions. And so I look at that in a little bit more detail. And this can be one of the harder things we've done so far. So I encourage you to watch that video, or, the book has a pretty nice explanation of predicting the products when we have to proceed through this anti-periplanar transition state. All right, so one thing to keep in mind, we only have to worry about this stereospecificity when there's only one beta hydrogen, right? In this example, I've got two beta hydrogens, and so we can make anti-periplanar transition states where this R1 actually ends up being on both sides. And so in this case, we do get both stereoisomers. And so we don't have to worry about the stereospecificity. We would have to look at stereoselectivity, right? And so we can't tell that from this example because we don't know what these R groups are. But so E2 reactions are only stereospecific, essentially when both the alpha and beta carbons are stereocenters, right? So just to try to differentiate between stereospecific reactions and stereoselective reactions, when we have a given substrate that can produce two different products, right? And so, for these E2 reactions, we're thinking about the cis and the trans, or the E and the Z isomers, then it's stereoselective. If we have a case where the substrate can only produce one stereoisomer, then that's the case where it is stereospecific. And again, remember, to be stereospecific, we can only have one hydrogen on that beta carbon, and actually both the alpha and beta carbons need to be stereocenters. All right, so another important feature of E2 reactions is what happens when we have a cyclohexane derivative, or we have cyclic groups. Remember that in order for an E2 reaction to occur, the leaving group and the hydrogen have to be periplanar. They have to be in an anti-periplanar configuration. It turns out that can only happen when the leaving group and the hydrogen are in axial positions on neighboring carbon atoms. And so from this conformation, we can have an E2 reaction when the leaving group is in an equatorial position. It's not anti-periplanar from a hydrogen atom, and so we can't get E2 elimination from this conformation. So we can get E2 when they're axial, we can't get E2 when they're equatorial. All right, and so as a result of this, if you remember when we talked about the groups coming off the cyclohexanes, we often talked about whether they were up or down relative to one another. And so it turns out that they have to be on opposite sides of the ring in order to get an E2 reaction. So only these hydrogens marked in red are able to participate in an E2 reaction. And so this can have consequences for what products we might get and when we're actually going to get an E2 reaction. All right, and so for an example of that, only one of these molecules can undergo an E2 reaction. So remember, to have an E2 reaction, the leaving group and the hydrogens have to be on opposite sides, right? One's got to be up and one's got to be down. So I think in this case, right, the chlorine's up, the hydrogens are up, right? And so there's no way to get an E2 reaction from this molecule, right? Now, in this case, right, the chlorine is up, both of these hydrogens are down, so these hydrogens could participate in the E2 reaction, and so we would get an E2 elimination from here, but it would have to be one of these hydrogens, right? This hydrogen, because it's on the same side as the chlorine, it also can't participate in the E2 reaction. Okay, here's another example of stereospecificity in these cyclic compounds. So in this first example, we only get one product, right? We only get elimination involving a hydrogen on this carbon atom, right? This carbon has two hydrogens, one's up and one's down. So because the chlorine's down, the hydrogen that's up, we can get elimination, right? But in this case, the chlorine's down, we've got this tert-butyl group up, right? So then the other hydrogen on this carbon atom must be down, but it's down, the chlorine's down, so we can't get elimination from this carbon, and so we only get the one product. In this case, I've got two hydrogens here, and so one's going to be up, one's going to be down. So the one that's down can participate in E2 with the chlorine that's up, and so we do get this product. But then we also get this product where, right, the chlorine is up, right, the T-butyl is also up, and so the hydrogen's down, so we get both products in this case. Another interesting feature of these reactions is, it turns out this reaction is very slow, whereas this one is very fast. The reason being, if you remember, the chlorine's got to be in an axial position. Well, if it's down and it's axial, then that means when this chlorine is axial, this T-butyl is also axial, right? And we know, right, this big bulky T-butyl group hates to be axial, and so it doesn't spend very much time in a conformation that can that has the chlorine in an axial position and can participate in an E2 reaction. Therefore, this E2 reaction is slow. In this case, when the chlorine is up, and this guy's also up because they're on neighboring carbons, when the chlorine is axial, the T-butyl is going to be equatorial, and so, right, this molecule is going to prefer a situation where the T-butyl is equatorial, and so it spends most of its time in with chlorine in the axial position, and so it spends most of its time in a conformation that is possible to get an E2 reaction from. All right, so as you've seen, E2 reactions are quite a bit more involved than SN2 reactions, and so there's a lot of things to consider, right? Is my substrate stereospecific? Is it stereoselective? And is it going to be regioselective? And so it's really important to do a lot of practice problems so that you get more comfortable in predicting the products of these E2 reactions. And I have another video where we just look at examples of drawing products from E2 reactions, and where we'll consider sort of all of these factors that go into determining what the products are and what, if there are multiple products, what are the major products and what are the minor products.